Hello, I'm Michael Ernst. I'm going to be talking about how pluggable type checking is useful for programming, for teaching, and for research. The reason we're all here is that we're terrible programmers. Here's a screenshot of the Dutch National Railway website. It's a little bit hard to see, but the output of the Planner Plus application is java.lang.nullPointerException. This also happens when you're trying to get a ride share. And even more seriously, here is a security appliance, and its output is Java lang null pointer exception. So a null pointer exception can lead to an undisclosed security vulnerability. The fundamental problem is that Java's type system is too weak. It prevents some errors, like putting hello world into an int, but it doesn't prevent enough errors. At the bottom of this slide is a line of code that compiles fine. It probably runs correctly on every test on your development machine, but it can crash in the field. For instance, when you're running in a headless environment, because system.console can return null. So my proposed solution is pluggable type checking. That enables you to write stronger types, which are essentially specifications, and then type checking is verification that reveals errors. This is a static analysis, so there's no effect on execution. I'll be talking about one particular implementation called the Checker Framework. It's used at Amazon and Google and Uber and startups, at universities, at research labs, etc. It's fully compatible with Java. It uses a standard Java syntax, and your programs remain compilable with a standard Java compiler and runnable on a standard JVM. So pluggable type checking is useful for programming and for teaching and for research. Let me explain each of those points. For programmers, they get to find bugs in their programs, but this is actually much more than just a bug finder. If the tool issues no warnings, you have a guarantee that there are no errors of that variety. This is quite different than testing and bug finding tools. This also improves your documentation. Because the documentation is machine checked, you're guaranteed that it's complete, correct, and up to date. And the suggestions of the tool often lead you to improve your code structure and improve maintainability. This can also aid downstream tools like optimizers and analyses. There are some negatives. There's no free lunch. One downside is you have to write the types. You have to write down the specifications of what your code's supposed to do. And another negative is, like with every type system, there are false positives, cases where the code won't go wrong at runtime, but the tool can't prove that, and it tells you it can't prove it. We found pluggable type checking very beneficial for students. It's great for teaching them about specifications. Instead of just writing specifications down with paper and pencil, they can put them in their code, in the code they've written, and then have them verified. This helps them to iterate and understand until they get it right. And now they get excited about correctness and verification, which used to be dry and tedious exercises. You could also impose requirements on student code, like it be correct, and this exposes students to cutting-edge research. We did an experiment where some students used pluggable type checking and others did not. The ones who used it got higher grades, and they spent no more time on their assignments. Pluggable type checking is also useful for researchers who want to build a new analyses. Once you have an analysis idea, if you use an existing framework, you can very quickly prototype it. Our framework handles all of Java, so you don't have to do any extra work to get handling for generics, for type inference, inner classes, etc. This lets you do big experiments on existing code quickly, and that increases your impact. And that's the focus of this talk, building new analyses. So let's talk about one analysis you might imagine. The Java 8 introduced the optional type, which is alleged to prevent null pointer exceptions. Optional is a wrapper. So an optional may have present content or absent content. And there are three key methods. One is a constructor that takes a value and produces an optional. Another is present, which tells you whether the content is present or not. And the third is get, which gets the content, but should only be called if the content is present. If the content is absent, that's going to throw an exception. So at the bottom of the slide, you can see an example of using optional. A maiden name is a person's family name before they're married. Some people have one, some people don't. And so you might declare that as optional of string. So the purpose of optional is to remind you to do a check. On the left is code that doesn't use the optional type. We have a variable mname, and you might want to call mname.equals, but that could throw a null pointer exception because the maiden name might be null. So the way you're supposed to write it is to write if mname is not equal to null, then you can call a method on mname. We can write the same code using optional. You would write optional of string omname, and now to call equals you could call omname.get.equals, but this might throw a no such element exception. So you need to check before you make the call. The way you would check is you would say if omname.is present, then omname.get.equals. However, there's still a problem here, which is that there's a possible null pointer exception if omname is itself null. So optional is a little bit more verbose, it has a little bit higher runtime overhead, and it has twice as many possible exceptions. Sign me up! Sounds great. But if for some reason you have to use optional, you need to use it correctly. And the rules for using it correctly are quite complex. Here are the rules that were proposed by Stuart Marks. You should never, number one is you should never use null for an optional variable. Number two is you should never use optional.get unless you can prove that the optional is present. And then there are some other rules as well. And he's not the only person who has proposed rules for optional. Pretty much everyone with a blog has given guidelines about this. So all you have to do if you want to use optional is keep these rules in mind all the time you're doing programming, and then get them right. That sounds terrible. Let's try to enforce these rules. I think it's better to enforce these rules with a tool. So one thing that we can notice is, here I've highlighted some key phrases from these rules. And if you look at the ones that are absolutes, they're actually Dataflow or type system properties. You should never use null, don't call optional.get unless you can prove the optional is present, and don't use optional to wrap a collection type. So since these are type system properties, we can write a type checker to guarantee these properties. How do you define a type system? Well, this is very easy. It looks about like this. Just joking. That's if you're an academic and want to publish in some PL conference. Actually, it's super simple to define a type system, or really to define any static analysis. Here are the four fundamental parts. First, you define a type hierarchy that determines what the subtyping rules are. Then you define type rules that tell you which operations are illegal. Then type introduction rules that tell you the type of new values. And finally, you can have Dataflow that tells you the effect of runtime tests. So let's do this. Now, recall throughout the main rule for the optional type system, which is you should never use optional.get unless you can prove that the optional is present. And we'll go through the four parts of a type system one by one. First, the type hierarchy. A type hierarchy tells you what things are like other things or are subsets of other things. So for instance, every reptile is an animal, every mammal is an animal, every giraffe is a mammal. And on the right hand side you can see part of the Java type system. So a type hierarchy has two pieces of information. One is what are the types, and the second is what are their relationship. If it's lower in the type hierarchy, there are fewer values, there are fewer integers than numbers, fewer numbers than objects, but it has more properties. There are facts that are true about integers that are not true about arbitrary numbers, and facts that are true about numbers that are not true about arbitrary objects. So the type hierarchy for optional looks like this. We're going to estimate every optional value as either being definitely present or being maybe present. Maybe present really means I don't know anything about this optional, and present means I'm sure that this optional has content. So that's the type hierarchy. Let me explain the syntax now. You would write a variable declaration, something like present optional string maiden name. So the type is present optional string, and that consists of two parts. A type qualifier, which is written in using a Java annotation at present, and then a Java base type, which is optional as string. And so on the right-hand side, you can see the type hierarchy written out more completely. A full type would be maybe present optional string is a supertype of present optional string. Now you don't want to have to write those type annotations all the time, and so the default qualifier is maybe present. Usually when you have an optional, you don't know whether it's present or not. If you knew it was present, you wouldn't be using optional at all. So maybe present optional string, writing that is completely equivalent to just writing optional string. Now we're ready for the second step, the type rules. That tells you what operations are illegal. So recall the rule, never use optional.get unless you can prove that the optional is present. And I've put the type hierarchy in the upper corner for reference. So our rule is only call optional.get on a receiver whose type is present optional. Now here's an example call to get, myOptional.get, and get is a routine that takes one argument, namely the receiver. It's in a funny position on the left of the period. Here is how the get method is declared in Java. We have class optional of t, and then the declaration says it returns a t, and get takes a single argument, optional of this. In Java, you're allowed to write the this formal parameter, or you can leave it out. We're going to write it here because we find it useful. Now we need to specify that a call to get is only legal if the this has type present optional. So the only change we have to make is to add present annotation to the type of this. So now if we read this declaration, it says, when you want to call get, the this parameter must have type present optional of t. And now the type system, if your program type checks, then you know you're never going to be calling optional.get unless you can prove that the optional is present, just as our goal was. It turns out there's one other method you need to annotate, which is or else throw. It also needs to take a present this, or else your program might throw a runtime exception. So that's how we express all the type rules that we need. The third step is type introduction. This essentially tells you the type of new values. There are only two ways to produce a new optional. One is to call of, and the other is to call of nullable. Of takes a non-null value and produces a present optional. Of nullable takes any reference. The reference might be null, the reference might be non-null, and it produces an optional that might be present and might not. So we can write these annotations to express the specification. In particular, this is how you specify of and of nullable. Of takes a t and yields a present optional. Of nullable takes a possibly null t and it produces an optional of t, which means maybe present, means we don't know. And that's how you express the type introduction rules. Finally, there's runtime tests that may yield information about types. The checker framework implements a technique called flow-sensitive type refinement. The idea is that after some operation like a test, you can give an expression a more specific type. Suppose we have a variable x whose type is maybe present optional. We don't know anything about it. If you do a test, if x dot is present, then within the body, you can assume that the type of x is present. And then after the body, the type of x becomes maybe present again. In other words, a variable can have a different type on every line of the program. This is the way I think all type systems should work. I think it's crazy that they don't all work this way. So now we've designed this, let's actually implement this. So we're going to follow the instructions in the checker framework manual. So here's the checker framework manual, and there's a section, so we want to find how to create a new checker. Here's a section about how to build your own pluggable type checker. And first there's some propaganda that says writing a simple checker is easy. oops. There, the font's a little bigger now. That says writing a simple checker is easy. Here's actually a complete checker. Then there's some details about the architecture. It tells you the parts of a checker. Here are the parts that we discussed. You already know about this. And then, here, this is good. This is tips for creating a checker. So let's actually follow these tips for creating a checker and build one. So it says the first thing you should do is write the user manual. This is actually pretty important. If you don't know what you're trying to build, then you're unlikely to be successful building it. Here I've written the type checker for us. Written the manual for us. It shows the 7 rules. It says how to run it. It describes the annotations. You can see the hierarchy here. And it tells you what the guarantees are. So good. The manual is written. Let's go to step 2. Step 2 says implement the type qualifiers in the hierarchy. So let's look at what the manual says here. It gives an example, and so let's cut and paste this example because I think that's going to be an easy way to get started. So we're going to create a file called maybe present. We'll just paste that in and let's take a look at what it is. So the manual had showed us how to create a hierarchy with unknown sign and non-negative. And we're going to be changing that. So instead of unknown sign, we're going to define maybe present. And instead of non-negative, we're going to define present. It's in a different package. This is in the org.checker framework checker optional qual package. And this one is 2. And we need to update the manual. The value may be present or absent. So that's a description of the maybe present, and we'll also describe present. The value is definitely present. And we give a reference to the manual there too. And the last thing we need to change is that to say that present is a subtype of maybe present. So now we've defined the qualifiers. I'm going to put this one in a file called present. Okay, so now I have 2 files, present and maybe present, and let's try to compile this and see if that compiles. Now, while we're doing that, I want to show you some code. So here is a person class. A person has a family name and a given name, and they have a maiden name, which is their family name before marriage, and it might be null or not. And then there's some getters. There's a constructor and some getters for this. Here's a client. Here's some client code. We have a method that is Jackie O that says whether this person is Jacqueline Onassis, and that's true if their maiden name was Bouvier. And so we can compile and run this, and if we can compile and run this, we get a null pointer exception because the person was Diana Ross. She happened not to change her name when she got married. We could fix this by saying if p dot get maiden name equals null, return false. And now if we run it, it tells us that Diana Ross is not Jackie O. You could also do the same thing with optional, And here we can see that we have a family name, a given name, and a maiden name. But the getter returns an optional string. And here and there's also a client that is testing whether someone is Jackie O. And here we're testing against Elizabeth Windsor. She's another person who happens not to have changed her name when she got married. And if we try to run this, we get a no such element exception. And so here we would want to do something like if p.getMaidenName, if it's not present, then return false. And if we do that, then the then they're different people. So you can see it's really easy to make mistakes, and you need to remember to get them right. So great. Let's take a look at the so good. We've now sorry. Okay, so we implemented the type qualifiers in hierarchy. This says you should also write some simple test cases. Here's an example test case. So I actually have that one. Here's that same test. It has it has a may be present. I'm applying it to integer just for simplicity here. And present. And so you can assign a may be present to a may be present. You can assign a present to a may be present. Subtyping permits that. You cannot assign a may be present to a present. That's an error. But you can assign a present to a present. So this is just tests of subtyping. And now if I run the subtyping checker with the qualifiers I just defined, it issues one warning, exactly the place it should. So in other words, just writing those two qualifiers, we already have a system that approves 3 of these 4 assignments and rejects the other assignment. Good. Now, next we can write the checker class itself. So going here, there's something that we can cut and paste. So that cut and paste is always good. So let's we're going to create the optional checker, and here again the package has to change. It's in this package, and the name is optional checker. Great. Now we can compile this. And previously I was using this complicated command. Now it's much simpler. I can just say minus processor optional, and we get the same effect. That's all we achieved there, really. So great. Now we're on step 4. We finished step 3. Step 4 is test infrastructure. I've already done that part. So the next step is annotate parts of the JDK. So you can recall that we did have JDK annotations that we did have parts of the JDK we needed to annotate. So here, this is the optional class from the JDK. So recall that we needed to annotate the get method. The get method must take a present optional, not just any old optional. And also recall that of gives you back a present optional, not just any old optional. And finally there was or else throw, and that also requires a present optional. Great. So if we save this and recompile, oh, I didn't show you, I've written some test cases too. And now I can run these tests. I didn't show you them before I did that, but now we can see that trying to call get on a present works, but trying to call get on a plain old optional fails, exactly as we would hope. So great. Let's go back. So next we have to implement the type rules, if any. We've already done that. All the type rules are already encoded in the JDK annotations. There's no more code to write. The same for type introduction rules. Those are already done. And the last thing to do is to implement Dataflow refinement rules. So let me show you a test case for that. Here is a routine with a class with 3 routines. One takes an optional string and just calls get. That's illegal. Another one takes a plain old optional, might be present or might not, but if it's present, it returns opt.get. Otherwise, it returns a non-null value. And this one does the same thing, but it has a negated test. So to express this, we're going to write this annotation. Let's read this slowly. This says that if isPresent returns true, then the receiver, this, must have been present. In other words, if isPresent returns true, the receiver of isPresent must have been present. So let's compile that change, and then we can run this test case. And now the type checker issues a warning about this illegal call and no warning about the others. So we've achieved flow sensitivity. So now we can, and that's it. We're at the end of the rules. So we can also see this on our example code. So here we had this person. If I had not made this change and we ran the type checker, then it issues a warning. It says you can't call get on p.getMaidenName because that might not be present. But if we comment this out and rerun the type checker, then it approves it. In other words, the type checker is going to tell you when you might have a runtime crash. So that was item 1 in Stuart Marx's. Sorry, that was item 2 in Stuart Marx's rules. We can also implement number 1 quite easily. Never use null for an optional variable or return type. In fact, that's already done. If I look at the optional class here, we've written non-null here. That means that you can never have null. So that's done. We can also look at number 7, which is don't use an optional to wrap any collection type. So the implementation of that is here, rule number 6. So here it's implemented. This says, is a type a legal type? Is it a valid type? Is it a type you're allowed to write? So we're going to test type. So if it's a collection and its type argument is optional, report a warning. Also, if the type is optional and its type argument is a collection, report an error. So this actually handles both rules 6 and 7 in Stuart Marx's rules. Okay, so that's it. We have written very little code, and we have a type checker that actually does all the things that it's supposed to. So we implemented it. So this is already distributed, but the point of showing you this was to show how easy it is to do. And in conclusion, pluggable type checking can improve your code. You can use the checker framework to create new type checkers that are featureful, effective, easy to use, and scalable, prevent bugs at compile time. You can create your own custom analyses. So I encourage you to try it out and use it. Thank you very much.